Research on clocks is to improve the precision of time measurement. By accurately measuring a periodic phenomenon with as high an oscillation frequency as possible, it is possible to increase the precision of a second. In 1927, the quartz watch was invented. In 1967, scientists defined a second using a cesium atomic clock, which has an error of only 1 second in 30 million years. This definition still stands today. In 2001, a revolutionary method was proposed at an international symposium in Scotland. A clock with an uncertainty of only 1 second in 30 billion years. This is the optical lattice clock. Optical lattice clock. Invention of a clock that only loses 1 second in 30 billion years. Katori was born in Sawara, city of Katori, Chiba Prefecture on September 27, 1964. He spent his youth in Akabane, Kita Ward, Tokyo, until junior high school. Katori bought electronic components in Akihabara and worked on them every day. He loved reading circuit diagrams. In 1983, he graduated from Ibaraki Prefectural Tsuchiura First High School. In 1984, he entered the College of Arts and Sciences at the University of Tokyo. He joined the Department of Applied Physics, the Faculty of Engineering, out of a desire to control atoms with electronics. In 1994, Katori earned a doctoral degree with a research paper on laser cooling of atoms in rarefied gases. The research he conducted at this time formed the basis for his later ideas. On the recommendation of his professor, Dr. Fujio Shimizu, Katori traveled to Germany to serve as a guest scientist at the Max Planck Institute for Quantum Optics under the supervision of Professor Herbert Walther. Katori was advised by Professor Shimizu not to participate in research on single-iron optical clocks, a kind of optical atomic clock which was the mainstream of research at that time. The problem with single-iron optical clocks was that, assuming the oscillation frequency could be measured accurately, a single iron had to be measured many times. 1 million measurements were required to improve the precision, which would take as long as 10 days. Katori witnessed researchers conducting such experiments in the laboratory next door. "I want to work on atomic clocks someday." But pursuing such work in Japan would entail starting this ambitious program from scratch. After his return to Japan in 1997, invited by Professor Makoto Gonokami, Katori took part in the Erato project as basic research group leader of the Gonokami Cooperative Excitation Project, Japan Science and Technology Agency. He conducted laser cooling and trapping of strontium atoms. Katori predicted theoretically and experimentally demonstrated that specific wavelengths exist at which the effect of optical trapping of atoms does not affect the transition frequency of the atoms. His work led to the later discovery of the so-called magic wavelength. Unlike the single-iron optical clock, neutral atoms confined in the optical lattice allow measuring thousands and millions of atoms simultaneously, dramatically reducing the measurement time. The pieces slowly began to come together. In 1998, the technical basis that was the essence of the optical lattice clock was successfully demonstrated experimentally. In 1999, Katori was appointed associate professor at the Department of Applied Physics, the University of Tokyo. In September 2001, Katori was invited to speak at Frequency Standards and Metrology, an international symposium on atomic clocks in Scotland. On the day before his presentation, Katori was examining strategies for successfully incorporating the magic wavelength into an optical lattice clock. It was a moment when everything was connected. Katori proposed his idea of the optical lattice clock. It was the very heyday of the single iron optical clock, when this approach was considered the only roadmap for the next generation clock. Nobody was thinking about the other schemes, such as optical lattice clocks. As Katori remarked, this research had value precisely because nobody else was doing it. In 2003, Katori experimentally confirmed the magic wavelength. In 2005, Katori succeeded in developing an optical lattice clock and presented his paper. In 2006, the International Committee for Weights and Measures adopted an optical lattice clock using a strontium atom as one of the secondary representations of the second, which is a promising candidate for a future redefinition of the second. In 2010, Katori took up the post of professor at the Department of Applied Physics, Graduate School of Engineering, the University of Tokyo. In 2014, Katori succeeded in developing an optical lattice clock with 18 digits precision, which is 1,000 times more precise than the cesium atomic clock. The principles behind the optical lattice clock involve irradiating an atom with laser light and extracting the eigenfrequency of atoms. Strontium atoms are fused into a vacuum chamber. Using laser cooling, the motion of the strontium atoms is stopped. A laser tuned to the magic wavelength is used to create an optical lattice by interference effect, which is a container for atoms resembling an egg carton. The strontium atom is thus trapped in an optical lattice. A separate laser measures the oscillation frequency of atoms. The magic wavelength discovered by Katori is the laser wavelength used to create the optical lattice. This strategy eliminates the wide range of effects that affects the eigenfrequency of atoms, enabling incredibly accurate measurement. By taking the average of multiple measured atoms, it is possible to determine the oscillation frequency of atoms in a short time. This frequency can be used to determine a more accurate length of a second. Today, Katori serves as professor at the Department of Applied Physics, Graduate School of Engineering, the University of Tokyo, and concurrently as chief scientist and team leader at RIKEN. He is continuing a broad range of research, including further improving the accuracy of the optical lattice clock and exploring the application of optical lattice clocks. In one such project, Katori used an optical lattice clock to test one of the predictions of Einstein's general theory of relativity, namely that time passes relatively slowly for an observer in a location of strong gravity. If differences in frequency caused by differences in gravity can be measured with precision of 18 decimal places, a height difference of 1 centimeter can be observed. Katori demonstrated this effect between the University of Tokyo and RIKEN, and between the observation deck of Tokyo Skytree and the ground below. Curved spacetime by gravity was observed in a short amount of time. This result implied that the optical lattice clock serves as a sensor. These possibilities in sensing raise the curtain on an age of next-generation spacetime information, in which crustal movements such as earthquakes and volcanic activity can be measured by clocks. Beginning in 2018, in collaboration with a wide variety of companies in the framework of JST Mirai program, Katori is devoting himself to research in sensing applications, starting a wide range of endeavors to contribute to the world by putting the optical lattice clock to work for society. In 2005, he received the European Frequency and Time Forum Award. This honor was followed by the Medal with Purple Ribbon in 2014, the Leo Esaki Prize in 2017, and in 2022, the Breakthrough Prize in Fundamental Physics. Katori is a recipient of series of prestigious awards. Advances in timekeeping are more than mere innovations. In every era, such changes have sparked a paradigm shift, redefining the second. Katori's research prefigured the day when the definition of the second would be accurate to 18 decimal places and beyond, into an unknown world. The road ahead may be steep, but don't hesitate. Take the first step forward. Without you, my young friends, further steps are impossible. So begin by finding a journey that is worth starting. If you can foresee the destination, it is less exciting. The road worth traveling is the one whose end you can't see. Look for projects that haven't started, which won't start unless you start them. I want you to aspire big dreams. You can only tackle great challenges when you're young. Katori expects technologies to be developed that use space-time information with an unimaginable accuracy now. The optical lattice clock that only loses 1 second in 30 billion years will surely give rise to new technologies that will take us to a world we have yet to see.